approximately equal to IE. So when VB is going to change with temperature, IC will change. You know, when VB is changing, IC will change. When the IC is changing, you have to cancel the variation in IC. So what will you do? I am going to add a diode at the base terminal to compensate for this change in VBE. So from this equation, you can also write this VB is equal to VD plus VR2. See, this side, if you see, VB will be equal to VD plus VR2. This side, if you see, you will get VB is equal to VBE plus VE. And we are using both. Okay, so VB is equal to VR2 plus VD. See here, the total applied voltage at the base is equal to voltage across the resistor R2 plus voltage across the diode D. So substitute this in the previous equation. So I will get IC is approximately equal to VR2 plus VD minus VBE by RE. So I get IC, the collector current expression I get, IC is approximately equal to VR2 plus VD minus VBE by RE. Okay, so if the diode and transistor are going to be in the same material as we assumed in the earlier case, the nature of variation in the VB is going to be the same pattern. So assuming that this transistor and diode is made up of the same material, we can expect the same temperature coefficient in both the cases. So if by that way, if you see, if the VB is going to change by a small amount, VD will also change by the small amount. And see the equation, I have VD minus VBE. If VB is increasing by 2, VD will also increase by 2. Effectively, when you subtract, it will cancel and IC will be approximately equal to VR2 by RE. See, logically, we are thinking how any change in the VBE voltage is going to completely be cancelled out by using a diode in the base side. I'll again explain this. It's very, very tricky. So I'm going to have a diode in the base side, which is series with R2. So this is VB, the total base voltage. The base voltage can be written as sum of VBE plus VE or sum of VD plus VR2, because in a loop, the algebraic sum of voltage is equal to 0, right? So if I consider this side, I can write VB is equal to VD plus VR2. If I consider this side, I can write VB is equal to VBE plus VE. So I write the expression for IE. I write IE is approximately equal to IC because the base current is very, very small. And then I write the final equation for IC. This equation is very, very important because we assume that the diode and transistor are made up of the same material. So both will have the same characteristics of variation in VBE. If the diode VBE is going to increase, transistor VBE is also going to increase. If the diode VBE is going to reduce, the transistor VBE is also going to reduce. So in that case, what happens? Effectively the behavior is going to be same, but our equation has the relation VD minus VBE. So effectively VD and VBE are same because transistor and diode characteristics are going to be same, so I can cancel it out. So effectively I can write IC is approximately equal to VR2 by RE. So IC is essentially maintained a constant. So IC depends on RE, RE is constant, and IC depends on VR2, VR2 is also constant. So whatever change in VB I am going to have in my circuit, I am going to maintain a constant collector current across my device. Okay, this change in VB due to temperature is compensated by change in diode voltage, which keeps the IC stable at the Q point. So any change in this VBE is automatically controlled by this VD. Either if the VB is increasing, this VD will also increase. When you subtract, it will get cancelled. When VB is decreasing, VD will also decrease by the same way. When you subtract, it will get cancelled. So in that way, what do I achieve? My Q point is exactly maintained in the middle of my DC load line, and constant collector current is going to flow throughout my circuit. When IC is going to be constant, the transistor is going to always work in the active region. In the active region, your transistor will effectively work as an amplifier. So all our goal is to make the transistor always lie in the active region. For this, first thing, we have designed the biasing circuit. Second thing, we have analyzed the Q point coordinates. Third thing, we have found out the stability factor to see whether the circuit is good or bad. And last thing, whatever circuit you take up for biasing, you should include all these bias compensation techniques. Either you have to use a thermistor, or you have to use a sensistor, or here now we are using a simple diode to ensure that the variation in VB is completely cancelled out in the